Welcome, everyone. I think this lecture is the only thing between you and the week of holiday, right? Okay, so let's get this over with so we can enjoy the holidays. Or not. Okay. Don't worry, I'm equipped for it. I don't have that many slides, so I can take my time. People were upset that I'm not finishing lectures on time, so today I made sure that I have enough slides, and I'm definitely going to finish them. Okay, welcome everyone. So just to give you an overview of what we've been doing, today we will talk about, this meeting is being live streamed. Okay, great. Can I click on okay? Ugh. Okay, I managed this. My God. Now I cannot do this. Help. Okay, so today we are going to see Verilog for Testbenches. But before we start with Testbenches, let's try to make a little recap of how we ended up coming here. I need the blackboard. Yeah. How we ended up coming here. So our goal is to understand how computers are designed, right? I mean, we don't really care so much about the Boolean equations and things like that. I try to make a case for you that knowing these will help you understand later on the steps. So we want to be building cool circuits, things that are of interest to us, and we had to endure a part of it. And I'm happy to say that it's almost over. So we have today. And then we will stop talking about Verilog. We will stop talking about the digital circuits as building blocks. We will have enough background so that we are able to build any and every circuit that we can make. And then after the break, we will start looking into processors. What are they designed? And we will surprisingly realize that after we had some brief introduction, our knowledge so far will be sufficient to design relatively complex processors with ease. And then we will first make a working version to understand how this thing works. And then we will complain about that one being not fast enough, not good enough. And then step by step, we are going to add more details to the story. So this is also what's been happening. When they first made a processor in the 70s, it was only a 4-bit version. Then came 8, 16, 32, 64. Then came other things. And the lecture will also start building up like that. So at the beginning of the lecture, we had very, very simple gates and things like that. And then we argued that what we have is combinational logic gates who had a number of inputs and a number of outputs. And those gates were great because the moment you knew what the inputs were here, you could immediately calculate what the outputs were, and Boolean logic and Boolean algebra came in to help because by using this Boolean algebra, we were able to make better circuits. What do I mean by better circuits? The logic functionality remained the same, but we argued that if we use fewer logic elements to realize the same functionality, we could do it smaller, faster, and with less power. And saying that, hey, just by being slightly more intelligent, by applying some mathematical formulations, if we can shrink this, make it better, faster, it's a more efficient design, which is something we all aspire to, sometimes because we are idealists, and sometimes because we want to make a product that is better than the rival companies, and we want to sell our product by saying that it is better. Soon we realized that the combinational logic circuits did a lot of things, and it's not so difficult to design them. Boring perhaps, but not so difficult. And we said, we want something more. And then we said there are these sequential circuits. And for sequential circuits, we have to realize we can not only rely on the present inputs, but we have to rely on some past, what happened in the past. We need to preserve the state. So we learned that there were these state-holding elements, and actually we talked about a bunch of them. We started with latches, we said there are flip-flops, there are other things, and then very shortly and without too much drama, we said that, hey, you know what? just let's concentrate on flip-flops, and those flip-flops who are triggered by a rising edge of the clock, whatever that means. And said, okay, now we have a circuit that is slightly more complex. It has a combinational logic part. It has a state holding element, and the output of it here has the present state. Great. And what happens with the present state? Well, we can take the present state and feed it back to a combinational logic, maybe get some inputs, and together with that, we can calculate the next state. And we argued that we can actually construct these things by building state diagrams or descriptions and come up with these. And these we called those finite state machines because depending on the number of state holding elements, a certain complexity or different number of states could be achieved. And then we looked at it and said, this is quite boring because, you know, it goes through a number of states. Why doesn't it also produce some outputs? And we argued that, hey, you can put a combinational logic that takes the present state and generates the output. We call these type of FSMs Moore. And there is a different version of them which takes the present input, the present state, as well as the present inputs and generates an output, and we call those Mealy type of FSM. So this is what we were discussing. Good so far? Okay. Now when we look at this, this is the generic way of how we describe FSMs, but not all of those sequential circuits look like this. If you follow my, let's take a different color. If you follow around here, there is actually a funny loop going on, right? So we start here, we go through the combinational logic, and then we end up at a second flip-flop. So in some cases, it's a little bit easier to tell what's going on if we take and draw this thing just like I made the loop. So you say somewhere here, there's a state holding element. So I'm drawing this one. And then it goes into a combinational logic block. I'm drawing this one. And then it continues and enters a next state holding element. And of course, these guys are driven by a clock, by a common clock. And they might have a reset if I want to set this back to something. And these guys are probably connected to something similar, or they continue going on like that. So I hope these two do not confuse you. Sometimes when we want to explain the finite state machines, we draw them like this in a circle. And sometimes when we want to talk about timing and other things, we draw it this way. They actually represent generically any kind of combinational sequential circuit combination. This far, good? Okay. So now we can just keep this one in mind. Now, we know how to design combinational circuits. We know how to add sequential elements so that from combinational logic, we can make sequential logic. And the argument was simple. If you know how to do both, you can design anything and everything. That's not a joke. That's not an exaggeration. The only thing that is missing from you and a top designer at NVIDIA, Apple, Intel is essentially experience. Okay? I mean, the basics that you need to have are already here. Now, what is the result of not having enough experience, or what happens if you are making mistakes? Well, we introduce bugs to our system, and we have to realize how to correct them. And we were making the argument, how can we do it? That was last week's lecture. So the cowboy way of it is, let's just build the circuit and see how it works. I'm usually right anyway, so it will just work. And due to the cost and time involved in making your own integrated circuits and the complexity, because they are growing and growing in complexity all the time, we argued that this is not the smartest way. Still could be doable. The next idea was, instead of building an actual ASIC, let's just use the same code base, the same Verilog description of the circuit, and use an FPGA, the ones that you are using in your exercises, to build the same thing, but at a lower capability, lower speed. This is done a lot. It's called emulation, FPGA emulation, for trying to run the system at speed. Still, because the environment is real and you have only a limited number of inputs and a limited number of outputs, the way for debugging things is a little bit difficult, because either it works great, which is what you expect, and then you don't need actually too much verification because it works great. And if it doesn't work, your hope is that it will say, hey, Frank, I'm sorry, you wrote this line of code wrong. Well, it doesn't do that. It just does something that you didn't expect, and you have no clue why. And maybe you want to break it down and try to look inside. And for those things, we argued, you could have, since you have the description of the circuit in computerized form, written in RTL code, Verilog code, you could use a simulator to have everything virtually. You have your code, that code runs on the computer, is emulated how it will work, and you can say, this is the environment, these are my inputs, ones and zeros, coming at certain rates and intervals, and then I know somehow I have like this magic oracle that tells me how an ideal circuit should work, and I could compare both of them and see what is happening. And we said that this will be a test bench. And today we are going to talk about how to implement this, or what kind of things we need so that we can implement it in Verilog. We are going to, this lecture or this type of descriptions are actually, can go on forever, because we made the argument that verification takes a lot of our time. And you can imagine that if it takes a lot of our time, there's also a lot being done in this case. So the arguments that here would take several lectures. Since you don't like boring lectures and you want to get to the fine stuff, we are going to try to keep the discussion to a bare minimum. However, this is what's going to happen. Somewhere, we have our circuit description. Oops, wrong one, this one. Somewhere, we have our circuit description. This is our sometimes we call it device under test, or circuit under test, module under test, under test. This is the thing that we have worked to create. And most of our circuits will have a sequential logic. So this means that they would need some sort of clock that is coming to them. So there has to be a clock source that generates this nice signal that looks like these coming waves. Maybe our circuit also needs an initialization, a reset signal. That's also okay. Those are like some special signals that we are adding into the descriptions. But what is interesting is we have to fit this circuit inputs, and depending on these inputs, what happens is going this way. At every clock cycle, I provide a new input. At every clock cycle, we calculate, whatever is here comes with combinational logic, gets memorized here. At the same time, what was here in the last cycle becomes available at the output. So at every change of the state, I consume one input and I produce one output. So if we are going to test this circuit, if we are going to see if it is working or not, what we will have to do is we will have to provide him a series of inputs, and every time we provide an input, we will also collect an output for the same time period. Notice that, because if it's not necessarily a combinational circuit, the input that you apply now and the output that you collect at the same time window may not really correspond to each other yet. Because this input, if it's a Mealy machine, yes, it will be from the same input. But if it's a Moore machine, well, it will first have to go in here, make a change, and then appear at the output. We talked about the rate of operation, and we said that the rate of the operation here depends on how much time I need to complete one set of operation between these two state holding elements. And we said, you know, these blocks have a worst case delay. We call it propagation delay. And it says, in the worst case, because there could be many different things it calculates, in the worst case, it will take propagation delay amount of time. Then we said, this flip-flop also has a propagation delay, so the flip-flop propagation delay. And while flip-flops are great, they are not perfect. They want to have the input a certain amount of time before the clock age comes. So you say, if I'm generating a clock signal, I have to leave enough time so that the flip-flop can propagate from the time the clock rises, this part, until this output. I need some amount of time. And after this time, I need at least the amount of time that this guy can definitely finish its job. And I have to make sure that I come sometime before the setup time of the flip-flop. And if I manage that, every calculation I can make will be correct. That's great. So this gives me the time that is needed, the period, we call this TC. And 1 over TC was giving us the frequency. Just to give you an idea, if this was 1 nanosecond, if this took 1 nanosecond of time, it said that I could do this operation 1 billion times a second, because 1 nanosecond is 10 to the minus 9. And if I'm doing it 1 billion times a second, we were saying that this circuit runs at 1 gigahertz. Are we good so far? Okay. Now, this is my device under test, the same device that I have here. So I have to provide these inputs. And for every input, I will get an output. Now, what I want to do is, I want to compare whether or not this output is the same as what I expected. Expected results. And this, for every input provided at the same time, I would get an output. And for that output, there would be an expected result. And I would make a count, you know, I would go over all of them. And in the end say, hey, I went through 1 million test cases. I applied 1 million inputs. I know for every input that I supplied here, what the output should have been. And I calculated it, I compared it, and I hopefully give a binary answer, right? Works, that's what we want to see. Or if it doesn't work, I want to see what time did it have a problem? For which input did I have a problem? How many did I have? Is it like 1? Is it 10,000? Is it 1 million? You know, so that I can either sleep or, you know, go back to work. Okay, now the question is, how do I get these inputs? We argued again last week that if it's a simple circuit, if it's a 2-input AND, 3-input AND, something like that, I mean, there's only so many possibilities it can have. And you say, you know what, we are a big brute person, we can just try each and every combination. If you can do this, great. Our life is easy. Unfortunately, the number of circuits that we can test this way is extremely limited. Only a handful of circuits, basically anything in your life that you are going to make or will be involved in that is worth designing, it will not be possible for those circuits to brute force this. So somehow you need to generate a number of inputs to these things. How do we generate them? Well, that's an interesting story. We didn't talk about it. We need to find some methodologies, which is not part of this lecture, which would be part if we were doing more about verification. But knowing that we only have a tiny fraction, and I'm not saying 1%, I'm talking about 0.0000000 until you fall asleep, 1% of all possible inputs is what we can afford to send. Why? Because I want to be finished with the verification within a couple of thousand years, okay? I cannot wait a couple of thousand centuries. And so we are pressed for time. And even if I collected all the computers in the world and let them only simulate my funny circuit, in many cases, it would take thousands of years. So I need to reduce or find ways how to find this stimuli. This is an problem on itself, but don't worry, it won't come to you as an exam question how to generate the stimuli. It's a combination of, let's say, known edge cases, known things where you know that it's difficult, it's one of those corner cases you have designed for, number of random inputs, with some quality control that tells you that everything is good. So, although we didn't discuss this much, at least hopefully I could make a case that there are some ways how these can be generated. How about the outputs? Well, for the outputs we said, there is going to be a golden model. So I supply the same inputs that goes to the circuit to the golden model, and I get the expected responses. That sounds very convenient. And of course, the big question is, where do I get the golden model? We gave some examples, known algorithms, known and verified algorithms and things like that could have mathematical models, algorithmic models that I can use in high-level languages like MATLAB to generate all the expected results that my circuit is supposed to generate. If you make a circuit that operates on JPEG pictures, you can say this stimuli is a collection of pictures. This one is your Photoshop or GIMP or whatever photo processing program. And these are the resulting pictures, your golden outputs. Whereas here we have to translate it, push it to the device, get the outputs, convert it to pictures, and then we can check them both together. The interesting thing is, the upper part, this part, we can do offline. I'm not saying we are always doing it offline. I'm just saying that this thing can be done once, and this stimuli and the expected responses could end up on a hard disk as a file and saying, hey, these are the simulation vectors. What happens throughout the development is that this part gets updated because you run your circuit, you are happy that it does it, but now you say, hey, I want to make it faster, I want to make it nicer, I want to make it smaller. So you iterate and try to make versions of it. You find bugs, you correct them, you want to rerun the same thing. The stimuli and the expected responses stay the same, but your circuit has now changed, so we run this entire thing once again. The lower part, this part, can be and is usually implemented as a Verilog file that we call the test bench. Now, it is not strictly necessary that all parts of the test bench are implemented in Verilog. It is also possible that parts of the stimuli generation and golden model are also sort of kind of done in Verilog. Happens. I've showed a slide with many different variations of the theme. Everything exists, but we are just concentrating on the smaller version where we have a virtual environment that instantiates our device. This is the one that we are developing, provides the inputs, takes the outputs, reads in the expected results, makes a comparison, and if needed, provides some additional signals so that our circuit can work properly. So this is what we are now going to see. Any questions so far? Everybody asleep? No? Okay, so just a second. Let's see, this works. Light black part. Okay. So our goal is to write this thing, and there's a number of things in it that we realize our current knowledge of system Verilog, we will not be able to do it. So how do I simulate our circuit? How do I apply the inputs? And how do I actually report to the outside? So for this thing, we will need a number of things that we still don't know how to do, and we are going to, in a very quick and circuitous way, introduce them. Now, this was setting the stage. So the idea, once again, just to repeat, we use a computer simulator to test the circuit. I instantiate the design. This is this part. I supply the circuit with some inputs. I look what it does and decide whether or not it returns the correct output. So this is essentially what I'm doing. Now, the important thing is, this test bench is a virtual environment. Any code that I write as part of the test bench is still written in Verilog, but we do not expect this to become a physical circuit. Unlike the rest of the time in this lecture, where I was always arguing there was this, funny circuit schematic with all these cockroaches and gates being connected by wires, horrible looking things, right? I said that whenever you write Verilog code, you should think that you are drawing that schematic. Every line that you write is either a logic gate, a module, or a wire connecting these things. Whereas once you come to the test benches, all of these things are virtual elements. We don't expect them to become a circuit. They are there to become a test bench. So they are not synthesizable. They don't have physical correspondence to something. This is important, and you will see a lot of constructs where you say, why don't I use this in circuit design? Well, the language is the same. It's still Verilog, but part of it is synthesizable, meaning that it can be turned into a circuit. And part of it is just for simulation purposes, modeling purposes, and those are not synthesizable. We will start with like the simplest thing, then we will continue making it a little bit more interesting, and finally, we will come to the self-checking test bench with test vectors, which essentially will boil down to this thing here. So let's go. The example is from the book. So instead of a huge processor, we have this gigantic function. And we are aware that the function is doing something very useful, so we call it silly function. And not surprisingly, because you are good at this, you'll realize that a single line of Verilog will be able to implement this Boolean equation, and we have 3 inputs and 1 output. Okay, that's great. So now this is modeling our device under test. Annoyingly, it doesn't have a clock or a reset. It's just a combinational circuit. However, it will do. Now, let's generate a test bench. Now, there's a lot of things here in one slide all of a sudden. So I'll try to go slowly over them. First of all, the module test bench, it's called test bench 1. It's like any other module because we are writing in Verilog. But it doesn't have any inputs. It doesn't have any outputs. A test bench is self-contained. It's a virtual environment that is the cloud around your circuit. Now, internally, I'll be using some wires, some values. And for those, I need to declare them. And funnily enough, some of them are rec, and some of them are wire. What's that all about? Well, we learned that anything which was declared in an always block had to be defined as rec, regardless of whether or not those are registered outputs or not. Anything that is not defined, not assigned to in a always block could be wire. Okay, why not? And the first thing that we are doing is we are instantiating the device under test, meaning that we are making this part. This is our test bench, in this case, test bench 1. And bam, we instantiated our circuit, connected A to A, B to B, C to C, Y to Y. And that D is a typo. Horrible. So, normally, we had this always block, and the always block triggered at certain instances. And once it triggered, we know that, it was meant as a how shall I say, as a virtual loop. Anytime the inputs changed or the conditions changed, it would trigger, but it wouldn't be executed on the program. It's just like telling the synthesizer what kind of circuit you wanted. And then you made all these assignments, and you could use cool things like if, then, else, case, and it looked great, right? We don't have an always here. We have its cousin, initial. It's the same deal as always, with the big difference that it only triggers once at the very start of your running this test bench. And when it reaches the end, it doesn't restart, it finishes. Okay? We don't need, this thing doesn't work for hardware. You cannot have this in a hardware kind of thing. There, everything perpetually runs, everything is in parallel. However, this is a virtual environment, and we say, okay, here's a block. It begins here, it ends here, and I will go through it one by one, and at the end, I'm going to finish my execution of the test bench. Nobody is expecting that this thing will become a real hardware. Good so far? Okay, we are going to get complicated. Now, I make my assignments. I say A0, B0, C0. Notice that now there is no excusing it anymore. Now I have to use blocking statements. There is no more blocking, unblocking controversy. At the unblocking assignments would be made at the very end. However, I'm doing this because I want an ordered number of events. I first want the input to be A0, B0, C0. Then I want to wait for a little while. Why am I waiting for a little while? Well, technically, what I want is, I applied my inputs here, and then I want some time to pass so that I can apply the second input. And then I want to apply the third input, and the fourth one, the fifth one, whatever. So two problems here. First, I want to make sure that whenever I apply the inputs, they are there the moment I apply them. I don't want like, hey, yeah, we are all friends. Let's wait until the end. We'll all assign ourselves together, right? So we say, the moment I write A0, B0, C0, A should be 0, B should be 0, C should be 0. Definition of blocking statements. Now, I managed this first part actually very good. If you are on a time scale, initially, so we started here at, I'll just raise this so that we don't have to blank it. At T0, when the initial started, I said, okay, A should be 0, B should be 0, C should be 0. And yes, they are like that. But now I want that time advances. And this is not synthesis, this is just the environment. And I need some sort of element that says, wait a little bit. And this hashtag 10 says, wait 10 time units. So now time will become 10 when I reach here. What is the unit of 10? Well, technically speaking, at the beginning of the Verilog module, I could define what my time unit is. I could say, you know what, 1 unit should be a nanosecond. Then I could also specify what's my resolution. And I could say, hey, you know what, let the smallest time step be, I don't know, 100 picoseconds. There are always some defaults, and in these examples, you will always see them as nanoseconds because it's a value that is close to the values of the technologies we use these days. They can be changed. We are not talking too much about that. You can always assume they are in nanoseconds. If not, you will be notified or there will be some comments explaining how we changed that. Okay, now we are at 10 nanoseconds, and I'm making a change. I'm changing C to 1 here. Well, what's the value of A? Okay, it's too boring for you. I understand. Nobody wants, like, Frank, I mean, ask me a real question, I'll answer. For something as simple as this, I'm not moving myself. Fair deal. Okay, now I wait 10 more. So time advances, T20. Now we make B1 and C0. Okay, so A still stays 0, B becomes 1, and C becomes 0. Then what do I do? Well, I wait 10 more. And now A is 0, B is 1, C is 1. And then, my God. And now A is 1, B is 0, C is 0. Now, all of a sudden, hopefully, some of you in the audience said, thank God I only have 3 inputs. If I had 50 inputs, Frank would be writing here 2 to the 50, meaning 1,000 times, 1,000 times, 1,000 times, 1,000 times, 1,000 lines. And that would look like a very, very, very difficult and boring thing. Hopefully, some of you are saying, this is not the way we are doing things. Who thinks we are doing this way? We are not doing it this way, okay? Hopefully not. Okay, but you get the idea. Now we have actually achieved the part of applying the stimuli. How do I generate the stimuli? Well, I wrote it inside to the code. Somehow I wanted to apply 0, 0, 0, then 0, 0, 1, then 0, 1, 0, 0, 1, 1, 1, 0, 0. You know, I'm going the binary sequence. And I realized that since there's only 8 possible inputs, this should be easily doable. Yes?
Why do we end at the why do we wait at the end?
This one. Just because we like copy paste. You know, while you're writing it, most probably, I mean, me, I can definitely tell you, the one who made the slide was just, you know, Control Z, Control V, and writing it. Yeah, you're right. I mean, why do I wait? I mean, just let's end it there. Well, maybe I also want to leave some time so that I apply the input, but I may want to leave some time so that the output can actually get calculated. We are going to come to that in a second. Now, this is what we call a simple test bench. It's very simple because it instantiates the design under test. So this is what I wanted here. It applies a series of inputs, but the inputs are, you know, sort of kind of built in. And what do I do with the outputs? When you come back here, you realize that you apply these inputs. Applying these inputs would mean that this output here would also get changed. But I'm not doing anything inside the test bench to do something with it. What do I rely on? I'll say there's a simulator, and I have this user. I pay him a lot of money, so you should look at the waveforms. And, you know, I will make 1, 0, 0, 1, whatever. And hopefully, the person looking at the output of the simulator is smart enough, and he can figure out if everything is okay. So the outputs have to be observed and compared using a simulator program, some sort, or personally, you should have a look at it. Now, this is the part of the initial statement. It's very similar to always. It doesn't need any trigger. It doesn't need any sensitivity list. Why? Because it immediately triggers when you start it, and it triggers once, and it will never trigger again. So what's the point of defining it? The moment the simulation starts, it starts doing its job. When it's finished, it's finished. And this one, we were hashing on this for quite a while. We said, hey, these statements have to be blocking. Because if they don't block, I will not get this, first this, then this, then this, then this. So we are moving from one to the other using these statements. So, oops, that brings us here. Another 10, we move from here. Another 10, we move from here, etc., etc. Questions? The only thing is, Frank, I hope you're not doing this the entire day. Okay, now we can get a little bit better. Question, sorry, yes. This one. No, this is the one. This is the one, this is the new one. So now it's exactly the same, but now we are also adding the comparison in here. We are saying, hey, is y equal to 1? Then comes this funny thing, $display. Well, $display is an internal function of Verilog, and it does type out to the standard output, in this case, the console of the simulator, whatever message you have. And in this case, we are nice enough, we say, you know, the vector 0, 0 failed. Okay, and then the next time I check, and I know that the output should have been 1 here, and I encoded it into the test bench itself. And now I know that the output should have been 0, and I'm checking if this is the case. If this is not the case, then write this. And then I run the next one, and I know that the output should have been 0. And if it's not the case, write this. Now, this is slightly better. Answers your question, right? So instead of me checking this thing, I am doing it. So it includes a statement to check the current state. The $display, there is roughly 50 of those helper functions in Verilog. You don't need to learn, memorize all of them. We are going to see a couple more. They will write a message in the simulator on the console of the simulator. However, it's even worse than before, right? I mean, it will automatically test and report to you what the thing is. Just imagine that you want to test an NVIDIA GPU using this type of code. It will be a couple of billion lines long. And since you make a mistake every 20 lines, it will have so many mistakes in it. You are not going to have a nice life. So this is where we realize we might need something else. And actually, this is an excellent point to take a break. So after the break, we can talk about the next best thing, a complete test bench that can read test vectors in, both for stimuli and expected results, and tell us more about what we are doing. Sorry, I'm 2 minutes too early. Okay. I was invited to join a beer garden. I said no. So, no? Okay. So we are trying to make these test benches because we realize we are unable to write code that functions properly. And we need some automated ways for making sure that we did the right thing. And we saw a couple of examples right now. And I hope you also agree that those things weren't that great looking. They look like a lot of work for us. I mean, I don't want to do more work for writing verification test benches than actually writing the code. So here is what we want to do, a little bit more elaborate test bench. We want to have some test vector files that contain the stimuli and maybe the expected results at the same time, read them in, apply them at the right time, and you know, generate all the rest. I don't want to say like, wait 10, do this, do that. I want to have a sequential circuit. I want to have a nice clock signal, maybe an initialization at the beginning that makes sure that we start from a known state. Yeah, so generate clock for assigning inputs, reading outputs, read test vectors, assign inputs, get expected outputs from the device under test, compare outputs, report errors, do all the dirty work for us. The only thing that we need to somehow provide them is, well, we need the inputs and outputs for everything else to run, but I want to do this part completely in Verilog. And we saw some fancy things, and the moment you realize that I can write things to the standard output or stuff like that, maybe I can do even more. I know a couple of you are thinking like, maybe I should write an operating system in Verilog. You can do that, probably. Nobody has tried it, thankfully. Okay. Now, the first thing that we have to realize is everything in a sequential circuit is broken down into these time steps. With the rising clock edge, we start making things available. Then we have some time to do the useful work. Then the output should be available. And then the next rising edge comes so that we can trigger the next set of calculations. Now, there's something useful in using only one clock edge, because we only have to care about the rising time here. I mean, whenever this thing rises, we do something. We don't really care what happens when the clock falls. But we want the clock to rise again, so at some point it has to fall, okay? I mean, it's pretty useless, it's falling, and it's not really helping us do anything because we are specifically only using rising edge triggered flip-flops. And so sometime within this period, in this 1 nanosecond, 10 nanosecond, whatever, the clock, once it, let's say this is time 0, and the next one will rise at time 10, somewhere between there, the clock should fall. Okay? I mean, it will happen. So when you are looking at it now, we have this test bench, and the test bench will apply inputs every cycle, every step of the way. We'll be applying the inputs, and then we will check the outputs, and we will continue to do so until all our vectors are exhausted. We might have 5, we might have 65 million, okay? But for every one of them, we are going to do exactly the same thing. Clock will rise, we will wait some time after the clock to apply our inputs, and then we want to check the outputs before the next clock event. And every cycle for cycle, we'll be doing this thing. Now, notice that when the clock rises, we want to give the inputs a little bit of time afterwards so that I can differentiate between things happening due to the state holding, I mean, due to what comes from the state and due to what comes from external inputs. I don't want to mix these two. I say, because the inputs that arrive at this time, these are, if I'm a Moore machine, for the next cycle. They won't become immediately visible. If it's a Mealy machine, this input will, in the same cycle, already change the output. Is this okay? Shall I repeat it? When you apply the input within this clock cycle, after the clock edge has risen, the only thing that happens is at rising edges, right? So when you apply this input, it's actually this edge, the next edge, that will take the input and do something with it. Because this edge has already passed. To make sure that this edge has already passed, we want to separate it. We don't want to apply the input at the same time as the rising clock. We want to have a bit of separation between the two. Does that make sense? Yes?
So if this would be for inputs and if the outputs we check for all the inputs, this would only be the case like on here if we have medium.
So let's go to the Moore and Mealy machine once again. Maybe, okay, forget about the loop inside here. I'm too lazy to draw it again. Sorry about that. Okay, now, when you apply the inputs, these inputs will go through a combinational logic and will end up at a flip-flop. Okay, so the inputs will end up being useful at the end of that clock cycle. So the moment that you apply it, it takes still some time. I mean, this is the point where they will have an impact in the internal state. Now, looking at the outputs, if it's a Moore machine, the output will only come from the state. So the earliest the state, the input can affect the output in a Moore machine would be the next cycle. However, in a Mealy machine, there is a sneaky part, right? The input can directly go to the output. So, Mealy machine, if you apply the input here, this output could already be affected by the input in this clock cycle. If it was if it's a Moore machine, it would have only come in the next clock cycle. Regardless, we want to have a distinction between this clock cycle. I mean, what happens with this clock? This clock edge is taking what comes before. So we want to make sure that we are applying this after the last cycle, once the entire event is done a little bit. So I'm creating a bit of separation. Okay? Yeah.
For the test inputs, they have to test all the inputs for all the different states you can have in the machine?
Well, that would be exhaustive testing, right? So we talked about that. That will prove to be impossible for most circuits. There will be very few circuits where we can do this, because if you have, let's say, n inputs, you have 2 to the n possibilities. Then you have m states times 2 to the m states. If you have, I don't know, 30 states input, 30 state holding flip-flops, 2 to the 30, and then you have 30 inputs, 2 to the 60, that's a million times a million times a million possibilities.
So it's important then which order you put in the inputs that could affect which state you get, depending on which order you give it.
Absolutely. Absolutely. This thing is crazy. You know, the number of stimuli to choose is not an easy task at all, because you are choosing such a small fraction of all possibilities. It's actually an unsolved problem to say, hey, given a circuit, given any description, what would be the complete set of inputs so that I know this circuit has no bugs in it? I mean, that's an open problem to be solved. We had a couple of slides before in the lecture before that. It's a very good question. Yes? I like it. What happens if you don't have this separation? Now, it's always like, you know, you have this entire period of time where you can do something, and please don't do it here. What happens if I do it here? Bad things happen. The bad thing that can happen is if it happens exactly at the same time, it could be that this input comes before the clock is evaluated. So you could actually end up having the input that was meant for this clock edge get sampled from here. So this is the first problem. The second problem is, while we are designing these circuits in RTL level, when we are simulating it at the RTL level, meaning that this is the HDL code, we don't really have any delays. Things happen instantaneously. So there is nothing happening in the combinational logic. This propagation delay doesn't happen unless this thing is already mapped to a technology, to an FPGA, and has real delays in it. Once you have real delays, ironically, it can happen that clock can also get delayed, and maybe not by the same amount as the data. So you might actually end up overtaking one another. So you want to generate your test benches in a way that there is a nice and clear separation between the two. The real problem is you will have a whole time violation against this flip-flop here, against this state here. So this is actually why we are leaving some additional time. I don't want to get too much into it. I don't want to involve setup and hold times in the test bench as well. Let's just agree that let's leave some separation between them. And the way we are going to do it in the test bench is going to be slightly entertaining. That's why I'm talking about it so long. Now, we need to have a test vector file, because I don't want to go into the code every time I'm changing these vectors. Notice that it could have been a very large number of vectors. Maybe I run the simulation with one set, and then I want to change these vectors. Maybe I want to do a quick test with only 1,000 vectors, and then later over the night, I want to run 15 million vectors. So rather than rewriting the code, maybe I want to have them separately in a file that I can just read in, which would be so nice. Now, this is nice. I need to generate a test vector file somehow. Well, the somehow could be that I use a golden model. It could be that I picked someone extremely smart or someone who has way too much time and given him the, all the possible inputs, he sat down and calculated this. In our case, because the silly function is so simple, it's so annoying, really, there are 8 possible inputs, all of them are here, and I calculated, so this is ABC, this is Y, ABC, this is Y, there's a function for it, it wasn't so difficult to calculate, but you can see, regardless of how large and complex the number of inputs are, if I have, I agree. I'm offended now. I thought it's about me. Oh, okay. Anyway, so you can create any type of file. In this version, we realize that system Verilog, you can write actually the underscore as a filler element. So I could have written them just side by side. It would be difficult to read. And I said, okay, let me just write 111 and then underscore 0 so that I can actually separate them. How I create this file? In this case, probably I did it by hand. However, imagine that this is a more complex algorithm. It's a whatever bit mining machine. You could easily imagine you use MATLAB or Python to come up with the vectors that are the input and then the corresponding vectors that are the output and generate 1 or 2 files that contain this data. It shouldn't be so difficult. We are not discussing how we do this. In most of our exercises, this will be already done, or you'll see how we can generate them. Good. So any doubts on this? No. Let's go to the next one. So now this is the real test bench. Still no inputs and outputs. And now here I have a bunch of interesting stuff. stuff we haven't seen? Well, first of all, we are also declaring the clock and reset signals because somehow we are thinking this is something that has a sequential logic in it. Then we have a bunch of things, A, B, C, Y expected are rec, Y is still wire. And now I have two vectors, vector num and errors. They are 32-bit values, which is okay. And then I have something which looks very strange. I have a 4-bit value, which is called test vectors, which is an array of 10,001. This is an array, 4 bits wide, and has 10,000 elements. Okay, it's doable. We didn't see it until now. There was not much use for it when we were defining hardware. Here it will become very handy. Now, instantiate the device under test that we already know. So this is this part. We have our device under test. And now let's generate the clock. In this case, we are reverting back to always because we want to have the clock that continuously makes 1, 0, 1, 0, 1, 0. And how do I begin? Well, I'll start with clock is 1, wait 5, clock is 0, wait 5, I end. And, well, and then it always does this, right? So it goes 1, where is it? Did I? No, I didn't. Choke. So, time 0, clock is 1, wait 5, clock is 0, wait 5, okay, start again. Clock is 1, wait 5, clock is 0, wait 5, clock is 1, clock is 0. There you go. This will go on like this forever. It says always. This part. Why do I wait 5 and 5? Well, I want the period to be 10 for some reason. I mean, I decided that this circuit requires 10 time units. And why am I nicely symmetric? Any ideas? Do I care if this is 5-5 or 1-9 or 9-1? I don't. Okay, since we only care about rising edge clock, so this is what we were talking about here. I want to generate this for a period of 10, and at some point this has to fall. I don't really care so much that it is at 5, but why not? Let's be nice, let's be symmetric, let's not go crazy and things. It's nice, you know, like symmetric. If I were using the same amount of rising and falling edge flip-flops, maybe I would have said, I want to keep them balanced. Right here, it wouldn't matter. Oh, people are not so convinced. Okay. Now comes the fun part, or what Frank calls the fun part. At the start of the test, load vectors and also pulse reset does two things at the same time. So this process starts directly when we start. And here is the great command. Read mem_b, read memory binary, example.tv, test vectors, not television. And load this into the array that we have defined before, test vectors. Now remember that every line in this file, example.tv, had 4 values. And I could, in theory, hold up to 10,001 of those lines. So this single command, read mem_b, will slurp reading the entire file and assign it to my test vectors. Notice that Verilog is not, I mean, he doesn't care. If your lines contain 50 characters, he would have taken the first 4. If your file contains only 2 characters per line, well, the first 2 of those test vectors would be assigned. The rest would be unknown, X's. My test vectors were not initialized, so they were all filled with X's. The moment I read this file, a certain number of them will be overwritten with the contents of the file, The rest of them will stay in the memory as X's. Yes. Zero, nothing. The underscore is just for the readability. It's a part of, when we were defining the number formats, we also use that. Underscore is a special character for Verilog and System Verilog, where they use it to, make numbers more readable. So you could have put 15 underscores in between, or 0 underscores, wouldn't have mattered. Just didactically, it's much easier to say this is the input, this is the output. Notice that I could have also read them from 2 different files. I could have an inputs file and expected outputs file. I mean, that's also possible. And then I initialize 2 values, vector number and errors. Okay, why not? At the same time, remember that I may want to have a reset. So you say, okay, let's pull the reset. Now look at this. This is crazy. Weight 27. Why 27? Well, I raise the reset here. And so this is 10, this is 20, and this is 5, and this is 2. And then I release it. Why? So that with the next clock cycle and a little bit before, I start nice and fresh. I don't want to change it right here. So this is, in this case, why sneakily I did this part. It's for initialization. I mean, it's just the initial state. There is this like wind blowing. Okay. Now, this is great. Apply test vectors on rising edge of the clock. This is where we are cheating, right? We wait always at post-edge clock, so we wait until this point comes, but then we cheat. We add this, do you see number 1? We wait by 1 unit. So you wait until this thing comes here, ta-da, and then we wait 1, so we move a little bit away from the edge. This is what I was trying to explain. I am applying the inputs with some delay after the clock. So the inputs, try not to change them at the same time with the clock. I mean, you could change them anytime you want, just don't change them at the same time with the clock, set up, hold, and everything. So ideal circuits, like the ones we are using, are immune, but real circuits may suffer from hold violations. This is the reason why we are separating them. Does it matter if it's 1 or 2? No, it doesn't. That's not a question. Okay, but now, look, this is extremely cool. What happens is, I have this combined vector, A, B, C, Y expected. Remember that putting things into the curly braces, this part, what is it? A, B, C, Y expected. Generates a vector of 4 bits, 1, 2, 3, 4, and it composes them. You should remember this from the time when we were looking at the combinational circuits. We could combine multiple single bit values together like this. And now I assign everything to test vectors. Notice that this was a huge array of 10,000, and each test vector was 4 bits. Which is fortunate because I'm assigning it to 4 bits. And I'm not taking any one of them. I'm taking a specific one, namely the one which was called vector num. So this is a number. It was 0, 1, 2, 3, 4, 5. I don't know. At some point, this will be test vector number 3. Should, whatever the value is, should apply to A, B, C, and Y expected. What are these? Well, if you go back, the input of the device is A, B, and C. So these inputs would come directly from the test vector, whichever number, right? So this was the vector num. Right? So one by one, I can go through the array through like that. And initially, the vector num was 0. So the first vector I'm applying would be the 0th element of this array here. So test vectors was an array of 10,000. So the first 10,001. So the first one is 0, the next one is 1, the next one is 2, etc., etc. So the first one I applied is here. And when does this assignment happen? Well, we wait until the positive edge of the clock. We wait until here. We wait one more tick, and then we make the connection. We assign the values at that time. We are making blocking assignments once again, because in test benches, we need blocking assignments. There is no discussion about blocking, unblocking anymore. These are all blocking assignments. I want that the moment I write this, the moment the simulator sees this line, I want these inputs to change, and whatever value the input should come here. And that's it. What do I do? Well, this is an always block. He will wait until he will wait until he sees another positive edge of the clock. And once the positive edge of the clock comes, he's going to do this again. And maybe, and hopefully, the vector number will have changed in the meantime. Oh, that's simultaneous. Okay.
Question. So the clock here, is it the same that our registers use, or is it?
Well, the clock is, we are talking about the signal that we have generated. Now, in this very particular example that I'm showing, the circuit doesn't need the clock. It's a combinational circuit. However, if it was a sequential circuit, and in most general case it is, we would probably feed this clock directly to the circuit as well. So it would be the same clock. Yes? Sorry?
Why did you use 27?
Why didn't we wait 30, or why did we wait 17?
No. Why did we wait 27? Why did we wait 27 and nanoseconds after the reset? Why exactly did it?
What do you want it?
I don't know,
Like, okay, but what's the number you want to write? There's one number that shouldn't be, everything else is okay. So tell me, not anything. You know, there's a difference between 10 and 11. There's a difference between 20 and 19. One of them is okay, the other one is not okay. That's a good one. Look, the story is here. So this is 0, this is 10, this is 20, this is 30. You don't want inputs to change at the same time as the clock. You want a separation between them. So waiting for the reset for 10 or 20 or 30 would not be a good idea. Waiting for 27, 11, 6, 34, where is Ankara? 6, everything would be okay. But not 10, 20, 30. Well, it's still good, but it's still like the worst thing you could do. You are just making things a little bit weird for everyone. Because at the same time as you are letting the reset, letting the flip-flop work and say, you are no longer in the reset state. Now you can wait for the clock. The clock came. Like, did I release the reset first, or did the clock come first? Let's not go into this debate. Like, you have any time you want, just release the reset, but not exactly at that time, if you please. Does that make sense? Sorry, yes.
We are coming into the reset exactly at 0.
Yeah.
That's no problem.
It's, you know, at this point, the circuit is in an unknown state. I mean, you can't make it any worse. You know, the reset is there to solve your issue. So the moment you pull the reset, the output will be at a known state. The point is, when you release it, the circuit will start functioning again. And before you let it function, you know, just give it some space to breathe, you know.
Then we also only start test vectors after the reset.
That's a good point. It will come, I mean, yes, hopefully. Hopefully. Okay? But it's a very good point. We should probably, before we are applying the first thing, check if the reset is not there. And a lot of test benches would do that. They would wait until, hey, if reset is not there, then let's apply it. Maybe this one already had it? No, it didn't. Okay. However, it does the opposite. This is where it gets a little bit complicated. Now, he wants to check the results at some point. Now, we have all the periods for us to check the results. We know that here we change the inputs. If it's a real circuit, there will be some propagation delay, and then I will have the outputs. Now, I could have checked for them at any point. It would have made sense to check them as late as possible. There was a good reason why we gave them this period, because we realized that this circuit needs this time to calculate its outputs. However, I can run the simulation at a slower rate, so it's not a problem. And just to make my life easier, I realized that there will be this falling edge event, and we say, let us sample the outputs at the falling edge. This is because we are lazy. And this is because we don't want to do too much complicated programming and things like that and enter an arbitrary delay. And we realize that sometime it's going to fall. And this is why we say always at negative edge. Why not? You know, wait a little bit for the outputs to settle. Then we are taking it. I will agree it's not the best way to do it, but it would work. The other alternative is wait for the positive edge, and then instead of waiting for 9, let's say wait for, instead of waiting for 1, we could have said wait for 9, wait for 5, wait for 6, something like that. In this case, we said let's wait for the negative edge of the clock. Not a big deal. No, okay. Now we are doing what was just being asked before. We are saying, hey, if it's not reset, because if it's reset, there's no point in checking the output. If it's not reset, let's do something about it. And then we start, and the first thing we are asking ourselves is why the output of the circuit equal to y expected? What was that? Where did we get this expected? Well, it actually came while we were reading the test vectors. It was part of the test vectors. I assigned it there. I didn't need it at the time, but since it was in one file, I read it out. And now I know what the output of the circuit is, y. I have read in y expected, and I'm just checking if they're correct. If they are not correct, I say, hey, for the inputs, A, B, and C, I can also format them. Look at this. Display. This is the message I give. %B will be replaced by the bit pattern. So B is for bits, A, B, C. So for inputs, this. Output Y was there, but I expected Y expected. And since I have an error, now I say, let's increase the number of errors by 1. No? If you say so, Frank. Okay. Now we continue. Since we have looked at one vector, let's increase the number of vectors. So let's move to the next vector. And now we are making the funniest thing there. If test vectors vector num equal, 3 times equal 4bx, what is happening? Now, our test vector was read into these test vectors, and it was a big array, right? Each one of them had 4 bits. So 0, 0, 0, _0, things. And at some point, we entered all the possible test vectors, but the vector was big. So the vector, so this was 0, this was 7. And then after, there were still many vectors, but they are all filled with x's because I didn't read anything in here. So everything after 8 until 10,000 will be full with x's. And I'm trying to detect this. Why? Because I want to know when my test completed. And I realized that, hey, I had a big array. I initialized a huge array. I didn't initialize it. I declared a huge array that had all unknowns in it. I read in a file that overwrote the first few with whatever values were there. And then the rest of them were all uninitialized. So it had the value of x. Now I just want to compare with x, because if the next vector contains all x's, so 4 bits, and all of them are x, then I know that I have reached the end of simulation. I just incremented the vector number. See, it's the new vector number, test vectors, vector number. If that equals to all x's, it means that, hey, all the vectors that I could have applied are finished. My file doesn't have any more errors, any more vectors. And then I say, hey, I finished my test, so many errors. And then I use another function to tell the simulator, dude, we are finished. This thing is over. I read enough vectors. I finished my simulation, and I'm able to, so I made these comparisons. I went through my array of inputs and expected results. I made the comparison. Now, the one annoying part is that triple equal to. So we have this, and we have the triple. Triple equal to allows you to make comparisons with x and z. Normally, this is not a useful thing. I mean, you cannot make any hardware with it. But there are times like these where you want to detect whether or not something is uninitialized, is not valid, there is something wrong, especially in test benches. It becomes handy. To be able to differentiate them, it is the version with 3 inputs. You might have also realized that the equality check we make with exclamation mark double equals, sorry, here as well. This lecture turned into whatever you say, Frank. Okay, so the commands actually have that can compare values that are x or z, in addition to zeros and ones. So if we go back, what we did, so this test bench generated the clock. So this is this part that we wanted to generate. So this part we have done. Now, the second piece was reading the test vectors and initializing and also applying the reset. So the reset part we have done. So this is the reset part. And then we have read in these vectors. So this part we have done. I've forgotten in the first part, we also had the instantiation. Yeah. Whoops. Dangerous. My God. We also had the instantiation, sorry. So this part is also done. And so 1, 2. 3, we assigned these inputs with some delay to the thing. So the reading was done, and now we assigned them, okay. Next one, compare outputs with the expected outputs. Yahoo. This part we have also done. And then the last part actually is to see if you are, if you are finished with everything, and if you are finished, we write a nice report. Tell the user, hey, we tested 1 million vectors, 0 errors, everything is good, go home and enjoy your life. Yay! You are hoping to do exactly the same. Okay, so the golden model is the ideal behavior. We still have to discuss how to do it. It's difficult to get it right, as you were talking before. In the worst case, you have to develop it from scratch. knowing something about the functionality, you have to write it. It can be C, Perl, Python, MATLAB, Verilog, Java. You're asking why Verilog. There might already be an implementation that somebody else did, and you're just doing a better version of it. So you can use the older one that works well and compare against the new one you did. And the most important thing here is we want to take ourselves out of the loop. We want to be able to run this automatically so that we can examine the results and do our debugging this way. We don't want to remain in the loop. Now, we already had this discussion. Why is verification difficult? Because if we were to take all possible inputs in, making some ridiculous assumptions for a 32-bit adder, we would wait 58.5 years. I'm proud to say I'm not that old. And so brute force testing is not feasible. We have to find a subset of these inputs. We are not discussing how we are doing it. But just to let you know that this is not as easy, so there is definitely work going into choosing the right vectors to test. Now, what did we learn? We learned today, this is the first time we are discussing about that Verilog has other uses than defining hardware that can be synthesized. It can be used for creating test benches. There are some other uses too. We will not go into them. We saw 3 classes of test bench. Applying only the inputs, checking manually, bad idea. Applying and checking results with inline code, meh. And then using test vector files, good idea. We saw a very simplified one. Usually the ones that we use in production are a bit more complicated. That concludes Verilog, ladies and gentlemen. Thanks a lot for taking part in it. You deserve a break, but after the break, things are going to get much, much more fun. We are going to look into processors, microarchitectures, assembly, how it all comes together, and then we will build processors. Enjoy your break. Thanks a lot.